All right, today we're diving into something truly ambitious, a real moonshot of an idea. It's called Project Suncatcher, and it's all about the quest to build AI among the stars.
AI's potential feels limitless, right? But its hunger for energy, not so much. It consumes a massive amount of power and resources, and that creates a fundamental problem. How do you scale it? So the question that's driving some really forward-thinking research is this. If we really want to unlock AI's full potential, do we need to start looking up?
Well, for one research project coming out of Google, the answer is a big, resounding yes. They're betting that the next frontier for our computing infrastructure isn't here on the ground, it's the final frontier itself, space.
So why on Earth, or I guess off Earth, would you do this? It really boils down to one simple thing: power, pure, raw energy. Our sun is the ultimate power source, putting out more energy than 100 trillion times all of humanity's electricity production combined. It is an absolutely vast, untapped resource just sitting there.
And look, the advantage you get from being in orbit is just massive. Down here on Earth, you've got the atmosphere, clouds, night and day. It all gets in the way of a solar panel. But you put that same panel in the right orbit and suddenly it's getting unfiltered, nearly continuous sunlight. That makes it up to 8 times more productive. That is a game-changing leap in efficiency.
Okay, so this huge potential is exactly what's fueling a brand new research moonshot. So let's properly introduce it: Project Suncatcher. So what is Project Suncatcher really? Well, at its core, you've got to picture these constellations of satellites, all powered by the sun. Each one of these satellites is packed with Google's powerful tensor processing units, TPUs for short, and they're all connected to each other with lasers. The goal? To create a massive, scalable AI data center just floating in orbit.
Let's just break that down into the key pieces, right? You've got 4 main ingredients. First, you've got the satellites themselves, and they fly in these really tight-knit groups. Second, the brains of the whole thing, the TPUs on board that are doing all the heavy lifting for machine learning. Third, you need a nervous system, and that's the free space optical links, basically laser beams that let the satellites talk to each other. And finally, the lifeblood, that constant, reliable solar energy.
I know, this probably sounds like something straight out of a sci-fi movie, but it's actually grounded in a long history of taking on these impossible-seeming projects. This quote really puts it into perspective, placing Suncatcher right alongside the efforts that gave us large-scale quantum computers and even Waymo's self-driving cars, ideas that seemed completely nuts before, well, they weren't.
But of course, a project this huge comes with some equally huge hurdles. The team's research paper lays out what they call the 4 great challenges that have to be solved for this to ever become a reality.
First challenge: how in the world do you get data center speed without any wires? A data center on the ground is all about these super fast, high bandwidth cables. How do you possibly do that between satellites zipping through the vacuum of space?
Okay, so here's the deal. High bandwidth needs a really, really strong signal. But basic physics tells us that the signal gets weaker super fast the farther you go. So what's the solution? It's actually kind of genius in its simplicity. Just get rid of the distance. If you fly the satellites in a super tight formation, we're talking just a few kilometers apart, you can bridge that power gap.
And you know what? The early results are just wow. A proof of concept they built in the lab has already hit 800 gigabits per second with just a single pair of transceivers. That is legitimate data center level speed. All right, so you fly them super close together. That leads to the next, very obvious question, right? How do you manage that whole orbital dance and keep hundreds of these things from smashing into each other? The answer, it turns out, is in the physics itself, plus some really clever computer modeling. By picking just the right kind of orbit, a sun-synchronous one, and running tons of simulations, the team found that the formation is actually surprisingly stable. Earth's own gravity does most of the work keeping them in formation, which means they only need to make small, little adjustments to keep the whole cluster together.
Okay, challenge number 3 is all about the environment. Space is just a brutal place. It's flooded with radiation. So can a super complex computer chip, like a Google TPU that's designed to live in a nice, safe data center on Earth, actually survive up there?
And this chart, this is pretty cool. It shows just how tough these things are. Researchers basically zapped the TPU with a proton beam to mimic years of space radiation. That first bar, that's what they expected to get over a 5-year mission. But look at the second bar.
The chips didn't even start to glitch until they were hit with nearly 3 times that dose. Turns out, they're surprisingly tough.
And that brings us to the final, and let's be honest, the biggest question of all, the money. Isn't launching an entire data center into space, well, astronomically expensive? Pun definitely intended.
Well, yeah, it used to be, but launch costs are absolutely plummeting. And this is the number that changes everything. Projections are showing that by the mid-2030s, the cost to get 1 kilogram into orbit could drop below $200. At that price, the entire cost of building and launching this system starts to look pretty similar to just the energy bill for a data center down here on Earth.
So with these 4 huge challenges looking, well, solvable, what's next? Let's take a look at the path forward for a project like Suncatcher.
So the roadmap is actually starting to come into focus. This year, they published the big research paper that lays all this out. The next major step is in 2027, a prototype mission with Planet to launch 2 satellites. That's going to be the first real test in space. And as we just saw, the mid-2030s is the time frame when the economics could really start to click into place. But the vision, it doesn't stop there. The ultimate long-term goal is to get to gigawatt-scale constellations. To put that in perspective, that's the kind of power a large nuclear plant puts out. And that would require totally new satellite designs where the solar panels, the computers, and the cooling systems are all one tightly integrated machine.
And all of this leaves us with one final and kind of mind-bending question. Look, Project Suncatcher is a total moonshot, right? No guarantees. But it makes you think bigger. If the future of our thinking machines, our most powerful AIs, is actually up in space, what does that mean for the rest of us down here on Earth? It's a pretty profound thought to end on. Thanks for tuning in.